Bismillahirrahmanirrahim. Welcome back to Mathematical Methods of Physics. Today we will study lecture number 32, which is the last lecture of the course, and that will be it for the course. Last time, in lecture number 31, in the second last lecture, we started calculus of variations, which is the last topic of the course of this course. We defined calculus of variations, basic definition, what basically the calculus of variation is, and then we defined the Euler's equation associated to the variational problem of integrals, equivalent forms of the Euler's equation, and then we studied two examples. One was the shortest path example and one was the shortest time example. Today we will continue with the same topic, calculus of variations, and we will study more examples basically. So today in particular we will be studying the minimal surface area problem, solid of revolution with least resistance problem, geodesics on the surfaces, and invalid variational problems. Alright, so these will be the four main examples which we will be studying today, and then that will be it for our course. And so let's start today's lecture with the examples. So first example is minimum surface area. Find the curve C passing through the 2 points A x1 y1 plus B x2 y2 such that the rotation of the curve about x-axis generates a surface of revolution having a minimum surface area. So this is the problem. You know that the surface of revolution, whenever we rotate a curve, a plane curve about some axis, it generates a surface which is called the surface of revolution. Alright, so we need to find a curve passing through two fixed points such that it generates the minimal surface area of the revolution, or it generates a surface of revolution that has a minimum area, surface area. When you generate a revolution, a solid of revolution, it has volume as well as the surface area. But here we are minimizing the surface area, not the volume. The surface area S generated by revolving the curve C defined by yx about x-axis is, you see here, this is our curve C. This is our curve C from A to B. If I revolve this about x-axis, then this curve downstairs will become this type of curve. Alright, and of course it generates a total area. This is a circle. It looks like ellipse from the side, but every point on the curve generates a circle. Every point on a curve generates a circle here. Alright, you are familiar with the revolution, surface of revolution. In calculus we study it in great detail, and we know what is the surface area as well, and that's why we are writing the surface area directly. How we get the surface area? Basically, we take the area of the cross section. Now if I take any point on the curve, it generates a circle, and the circumference of the circle is, outside layer of the circle is 2 pi radius. What will be the radius? Because at any point here x, the height is y. So y is the radius of that circle, which is the cross section of this revolution. So cross section of this revolution has a circumference of 2 pi y. If I integrate that from our point A to point B, it will cover the whole surface of revolution. Alright, so this is 2 pi y. This is the surface area of the cross section. If I integrate over the whole interval, it gives me the total area of surface of revolution. Now we know that from A to B, our x moves from x1 to x2, and our ds is again 1 plus y bar square root dx. Alright, so this is basically again the integral, and I am writing S for surface area. S is again a functional which depends on y of x. Now our function is a function of y as well as y prime. So to find the extremal yx, which is independent of x, the Euler's equation is d by dx of f minus y bar y prime partial f by partial y prime equal to 0. This is that equivalent form of the Euler equation, the first equivalent form in the last lecture which we studied. All right. If I use this thing and integrate, d by dx is gone, on the right hand side you will get a constant. This is the first integral. This expression is also called first integral of the Euler's equation, because we took one integration and we got this thing. Now if I replace the value of f and y prime, f and partial f by partial y prime, I'll get this thing, because this is my f. Without 2 pi, if you want to simplify it, you can write it without 2 pi. All right. The derivative with respect to y gives you just this thing, and the derivative with respect to y prime gives you 1 over 1 plus y prime square y prime. So that gives you the whole thing. If you simplify it, it's just y over 1 plus y prime square. So the missing details which are in minimal surface area example are, this is our Euler first integral of the Euler equation. All right, f minus y prime partial f by partial y prime is equal to constant. Here f is y times 1 plus y prime square. All right, so what I need is, I need partial f by partial y. So from here, partial f by partial y will be equal to, y prime will be equal to y times y bar over 1 plus y bar square root. All right, the derivative of this thing is 1 over 2 square root of 1 plus y bar square, and the derivative is 2y bar, 2 by prime. So 2 and 2 cancelled out, so you got this thing. So now if I replace this in 1, therefore 1 becomes f, which is y times 1 plus y bar square minus y prime, and partial f by partial y prime is y prime over 1 plus y prime square root is equal to c1. All right. Now if I simplify, if I multiply this 1 plus y bar square, this square root will be cancelled. So I'll get y times 1 plus y bar square and minus y bar square is equal to c1 times square root of 1 plus y bar square. Now you see, this is y bar square, and this is the same thing. So they are cancelled out. I am left with y is equal to, only y will be remaining, y times 1. y bar square minus y bar square, they are cancelled out. So you got c1 times y bar square root. So if I divide this expression on the left, I'll get 1 plus y bar square is equal to c1. So this is what I got. Now again, you see y bar is coming here. I can replace this with some parameter to make it easy. So here, if we let y bar to be letting y bar to be sine hyperbolic t, I will get y over 1 plus sine square is cosine square. All right, so I'll get cosine hyperbolic theta, not t, is equal to c1. So your y is equal to c1 cosine hyperbolic theta. All right. So again, to find x, here you must be wondering why we took sine hyperbolic theta. This is our own convenience. You can take, last time we took cotangent theta. The reason was this factor was being multiplied here. 1 plus cotangent theta is cosecant square theta, and when you divide by cosecant theta it becomes sin theta. So at the top it was just sin theta, and it looks good having sin theta up there. Here, because it's in the denominator, if I take the cotangent theta, it will become cosecant theta, and multiplying c1 cosecant theta, basically it is c1 divided by sin theta. So it's okay if you want to have the expression in denominator, you can have it. But now this looks better, c1 cosine hyperbolic theta instead of c1 divided by sin theta. Alright, so this is our own convenience, we can take whatever. Now again, dx is, for x I can write dy over y prime. As before, in the last example, in the last lecture, we did this thing. This comes from here, dy by dx is equal to y prime, right? So here, if I solve this thing for dx, it is dy by y prime. All right, so it's this comes from here. This comes from here. This expression. All right, so now, if I replace the values of dy and y prime, what is dy? Our y is c1 cos hyperbolic theta. So c1 dy is sine hyperbolic theta d theta, right? Divided by y prime is just sine hyperbolic theta, right? So from here, this is gone, so you got c1 d theta dx, all right? So on integration, you will get integration yields x is equal to c1 theta plus c2. All right, c1 theta plus c2, and now theta in terms of x can be written as x minus c2 divided by c1, right? So instead of writing the parametric equations, I can write it like this, because now theta can be written in terms of x very easily. So why not write theta in terms of x and replace theta in terms of x here, and you will get the explicitly y in terms of x instead of using the parametric equations. So therefore we get y is equal to c1 cosine hyperbolic theta, which is x minus c2 by c1. So instead of that, you got just one equation instead of writing the parametric equations. So again, this is a 2 parameter family of curves, because c1 and c2 are 2 parameters here, so this is 2 parameter family of curves, and where c1 and c2 can be obtained from the end conditions which we have obtained from end conditions. Conditions, what were those? Y at x1 is equal to y1 and y at x2 is equal to y2. So if you impose these 2 conditions, you can find the answer here. C1 and C2 can be determined from these 2 conditions, and that will be it. Alright, so it was not difficult at all, you see, finding the minimal, finding the curve. This is the curve which gives you the minimal surface. Alright, again, it's not a straight line, see. It looks like that straight line will give you everything, but it's not always the case. Alright, so this is what you got. I just explained it very briefly now. Here, in this example, I wrote t for my parameter t, and on the board I did theta, because it's just a parameter. It's your choice, whatever you want to call it. And in this example, somehow it gets eliminated at the end, so you are not even getting t or theta anything here. Alright, so this above equation represents a 2 parameter family of catenaries. The 2 constants c1 and c2 are determined using the end boundary conditions yx1 equal to y1 and yx2 equal to y2. Alright, so this was very easy example, nothing was difficult in here. Now let's move on to another example, which is a solid of revolution. Again, it's a solid of revolution with least resistance. Now we are minimizing the resistance, not the surface area or the volume. Alright, so let's move on to this example. Determine the shape of solid of revolution moving in a flow of gas with least resistance. Alright, so let's say a solid of revolution is moving in some medium, which is filled with the gas. All right, then, and we want to make the shape which gives you the least resistance. All right, so you know that usually our moving objects should have that shape to maximize the energy or efficiency or performance, whatever you can call it, like rockets in the air, you know, or airplanes and stuff like that. They are moving, and you don't want to get more resistance on the plane, right? It will cause more fuel, all right, to you. If the resistance is bigger, of course you need more fuel, you need more energy, your engine will be, you know, exhausted and stuff like that. So you need a shape of your object so that it moves very conveniently through the air, which gives you the least resistance. It will your moving object will become efficient on the fuel as well. All right, so whatever is your objective, we don't go in that. We just want to make a shape that gives you the least resistance. All right, so now what is the resistance? The resistance formula is the total resistance experienced by the body is F of Yx. It's a resistance, so it's a force, so I'm calling it force F of Yx. That is 4 pi rho v square y prime cube dx. Now again, I'm not going into the detail of this formula, all right, where we get it from. In physics, in any book of physics, you can easily come out with this formula. That's not a big deal. So you are having this from 0 to L, and again it's a solid of revolution. You have a curve Yx. This is a curve Yx, all right? It's moving in the gas flow, right? The direction of the gas flow is this. So of course a bullet-shaped thing, right? It's moving, so you want to minimize the resistance which is affecting the motion of this solid. All right, so again it's a revolution. Let's say the length is L from 0, so x goes from 0 to L. All right, and I need to determine this y of x. That gives me the least resistance. Now with boundary condition y0 equal to 0 and y at L is equal to, let's say it's r. YL is r, the radius of this of the other side. All right, here rho is the density. Rho is the density, v is the velocity of the gas relative to solid. All right, and your function here, because it's again it is again integral functional, which needs to be minimized. So again I need to observe the value of f here. So f is the integrand, which is y prime cube. And by taking this value of f, I can write the Euler equation. I'm not including this v square inside because v square is not y prime. It's the velocity of the gas relative to the solid, which is a constant. So this v is constant. That's why we brought it outside of the integral. This is not y prime. It's not the motion of. It's not the velocity of this object. All right. So it's not y prime. So now by taking this value of f, which is y prime cube. And again, it's independent of x, so the Euler's equation is, this is your Euler equation. Again, f is y prime cube, and the derivative of df by dy is this one, and you can easily solve it. So let me put the details on the board, how we are getting this, all the things. So the least resistance example. That's the reference of this calculation details. So my f is y and y prime cube. This is f. So from here, I can get partial f by partial y prime, which is three y prime square, right? Y is, as it is, so 3y prime square is the derivative, and what is and partial f by partial y is just y prime cube, right? So therefore Euler's equation, the first equivalent form will be easier here, d by dx of f minus y bar partial f by partial y prime is equal to 0. Let's use this one. Takes the form, this Euler equation takes the form with the above values of f and f prime. So f is y prime cube minus y prime as it is, and this is 3y prime square. This whole thing times d by dx is equal to 0. All right. So this is d by dx of, you see, this is y bar cube, and this is 3y prime cube again. You see, this is y prime and y prime cube. So this is minus 2y prime cube is equal to some constant. No, it is equal to 0. So now if you integrate, you will get minus 2y prime cube is equal to constant, and if you divide by this minus 2, you will get another constant. So you got y prime cube is equal to c1. All right, a constant. C by negative 2 is another constant. This is what you got. So I'm solving this for y prime, and for y prime I need y power 1 by 3. So y prime cube is equal to c1 by y. All right, and y prime is equal to c1 by y to the power 1 by 3. Because c1 is arbitrary constant, so you don't have to write 1 by 3 for that. Or you can say c cube is a constant, and now take the power 1 by 3, it will give you c1. Right? Just for convenience, we just don't bother if a constant is multiplied by another constant, or if you take the square root or cube root of a constant, it just remains constant. It's an arbitrary constant, so we don't bother writing it c1 to the power 1 by 3 and stuff like that. All right? So this is your solution here. So now by writing this y prime as dy by dx is equal to c1 over y to the power 1 by 3. This is a separable equation, first order separable equation. All right, first order separable equation, easiest of all. All right, so what we can do is I can bring this y on the left hand side and dx on the right hand side. Variables are separated. So once the variables are separated, you get to integrate here. If I integrate, I will get y to the power 1 by 3 plus 1, 4 by 3 divided by 4 by 3 is equal to c1x plus c2. All right. So if I multiply this 4 by 3 on the right side, if I multiply this by 4 by 3, then 4 by 3 times c1 plus 4 by 3 times c2 gives me another constant. So I can write c3 and c4 for that. So you can write y to the power 3 by 4 is equal to c1 4 by 3 c3x plus c4, right? Another constants. So y is equal to c3x plus c4 to the power 3 by 4. So this is the value of y in terms of x which I got. All right. So again by using the n boundary conditions that y at 0 is equal to 0 and y at L is equal to R, I can obtain C1 and C4. Let's do that. Now using y at 0 is equal to 0 and y at L is equal to R. These were the two n conditions in this case. We obtain y0 equal to 0 gives you 0 equal to C4 to the power 3 by 4. So this implies that C4 is equal to 0. So therefore, our y becomes C3x to the power 3 by 4. All right. Now use y at L is equal to R. So it means y is R and x is L to the power 3 by 4. So from here I can obtain the value of C3. So this implies C3 is equal to R to the power 4 by 3 divided by L, right? So therefore y takes the form C3 x to the power 3 by 4. So you got R outside and x by L to the power 3 by 4. So this is your y of x. All right, so this is the curve which gives you the least resistance through the gas, which has a velocity v relative to the solid of revolution. All right, so see again, at the beginning we did not know that what type of equation that will be. It was looking like a parabola, right? We said it may be a parabola, stuff like that. All right, so it did not come out to be a parabola. It's a power law. Right, so you see this is with the height r here. This is x by L to the power 3 by 4. You see, it's not a cubic equation, it's not a quadratic equation, it's not even 1/2, it's 3 by 4 power. So this is something which is power 3 by 4. So this is that curve yx, all right, which gives you the least resistance relative to the velocity v given by the equation. All right, so see, sometimes things we can expect that this should be something. Again, it should not be a straight line here. Again, we should not expect this to be a straight line. The reason is in straight line you might have something like this, but it may not give you the least resistance. All right, you see the least resistance come from something like this, something curved equation, right? That gave you the least resistance. So again, we can maybe guess something at the beginning, all right, but this procedure gives you the rigorous form of the equation, that this equation exactly gives you the minimum resistance or least resistance through a given gas medium. All right, so here the details were skipped, but I used I showed you now all the calculation, how we arrived at here, and then taking the integration I got this thing. All right, from here this is my curve, but using the boundary conditions we arrive at this solution, that yx is equal to r times x by L to the power 3 by 4. So this is the exact form of the your function y of x, which when rotated about the x-axis gives you a solid of revolution which has the least resistance passing through a flow of a gas, which is given, of course, in a given medium. It's moving, so this type of shape gives you the least resistance. All right, so this was another very interesting example of a variational problem or calculus of variations. We should have an integral form, and then that integral form has the associated Euler equation, and we use Euler-Lagrange equation to get our solution. We haven't solved the integral yet. All right, so again, the important thing is how we got that Euler equation, and as I said in the last lecture, we derived Euler equation not explicitly in my lecture, but in my handouts. If you see the handouts of lecture 31, there will be the proof of the Euler equation, how we got the form of the Euler equation. It's very easy proof, you should go over it, right? To convince yourself that these two are equivalent things. Minimizing or maximizing the integral is basically equivalent to solving our Euler equation. So you should motivate yourself through that proof, and then of course you can easily convince yourself that why we are solving Euler-Lagrange equation instead of minimizing or maximizing our integral. All right, so let's see another example. Geodesics. Geodesics are basically the curves on the surfaces with some special property. All right, so we will find that geodesic using the calculus of variations. So first of all, what is the definition of geodesics? If you have taken some course on differential geometry, then you must know what the geodesic is. All right, a geodesic on a surface is a curve. Geodesic is a curve on a surface along which the distance between 2 points of the surface is minimum. So geodesic is basically a straight, not a straight line. It's a curve that gives you the minimum distance on a surface. So the first example in the calculus of variation in the last lecture was the shortest distance between 2 points on a plane. So if your surface is a plane, then your geodesic is a straight line. All right, so you basically have found the geodesic on a plane. So on a plane it's a straight line, but if it is not a plane, it's a surface, then it may not be a straight line. Then you have to remain on the surface. All right. So if it's a curved surface, then moving from point here to here, you cannot go straight. All right. You have to make the curve which is on the surface. But it depends whether you go like this or straight there, right? So it depends. So let's see first example of a sphere. That if your surface is a sphere, then find the geodesic. All right. Find a geodesic on a sphere of radius a. Sphere of radius a, so you have to find the geodesic. Now because geodesic is a distance between 2 points, so we have to write the distance formula on a sphere. All right. So in spherical coordinate, when you have a sphere, so in spherical coordinates, it's convenient to write the spherical coordinates for the sphere. R, theta, and phi. The differential of arc length on a sphere is given by this one. ds square is equal to dr square plus r d theta square plus r sine theta d phi square. All right. So again in calculus 3 maybe, calculus of multivariate calculus, you might have seen this formula, or you should have seen this formula. So this is the differential of arc length in spherical coordinates. Now if I divide by d theta square, I will get ds square is equal to a square plus yes. Now here we have some simplifications. First of all, because the sphere has a fixed radius, the radius of a, that is fixed, so the differential of the radius will be 0, because radius is not changing. Theta and phi are changing, but the radius is fixed on the surface of the sphere, so dr will become 0. All right. So you are left with ds square is equal to r d theta square, rather not r, a d theta square. A square d theta square plus a square sine square theta d phi square. Now if you divide by d theta square, you will arrive at this expression. All right. Now here I need to find s. So what I can do is I can integrate it from theta 1 to theta 2. Before integrating, I need to take the square root, because I don't need this square here. Right? So take the square root and integrate from theta 1 to theta 2. You will get this one. Square root a comes outside. 1 plus sine square theta d phi by d theta square root d theta. All right. Here f is equal to a 1 plus sine square theta d phi by d theta square. So d theta is independent of phi, but is a function of theta and d phi by d theta. So denoting d phi by d theta is equal to phi bar, the Euler equation reduces to d by d theta of d f by d phi prime equal to 0. So this whole thing is independent of phi. Phi in terms, this is phi prime. So I have variables theta, phi prime. So there is no phi explicitly here. So derivative with respect to phi will be 0, but we have only two variables theta and phi bar. All right, so theta and phi prime. So if we have two variables theta and phi prime, then your Euler equation reduces to this d by d theta, because first expression is partial f by partial phi, which is 0. Then the second is d by d theta of partial f by partial phi prime is equal to 0. So from here partial f by partial phi bar prime will be equal to constant. That is, what is the derivative of f with respect to phi prime? So calculation details for the geodesic example on a sphere of radius a. So your f was a times 1 plus sine square theta phi bar square. Let me write it in this form. So this is a function of theta, phi and phi bar. So from here partial f by partial phi is 0 and partial f by partial phi bar is equal to phi prime, not bar, phi prime is a over 2 times 1 plus sine square theta phi bar prime square, and the derivative of this inside thing is 2 sine square theta phi bar. So 2 and 2 are cancelled out. So this is what you got. So our Euler equation, which reduced to partial f by partial phi prime minus d by d theta of partial f by partial phi prime is equal to 0. This will reduce to, because this becomes 0, so it is left, we are left with d by d theta of partial f by partial phi prime, which is equal to 0. So from here, if you integrate, you will get partial f by partial phi prime is equal to constant. All right, because derivative is gone. So now we have the expression for partial f by partial phi prime, which is this one. So from here, a sine square theta phi prime, sorry, a sine square theta phi prime over 1 plus sine square theta phi prime square is equal to constant. So k a constant. Now if I send it over there, take the square, I'll get a square sine 4 theta phi bar square is equal to k square times this root is gone, square root is gone, so I'm left with 1 plus sine square theta phi bar square. This is what I will get. So from here I can solve for this phi bar square. Alright, so sine square theta is common, so if I take sine square theta as common, I'll get a square sine square theta plus k square, and phi bar square is also common, equal to k square. So from this term and this term I took phi bar square common, so I'm left with sine square theta k square, but I took sine square theta as common as well, so I'm left with this one. So from here, phi bar square comes out to be k square over sine square theta a square sine square theta plus k square. Alright, so this is what you got. So now by taking the square root, I will get phi bar is equal to k over sine theta and a square sine square theta plus k square. This is what I got. Now sine theta, I can bring it outside and write cosecant theta. And now if I write this in terms of cosecant theta, I will get k cosecant theta over a square plus k square cosecant square theta divided by cosecant theta will make it cosecant square theta. Alright, and because cosecant, now I have to, this is d phi by d theta, right? Phi bar is d phi by d theta, so I need to integrate with respect to theta. Now here if you see, cosecant square is the derivative of cotangent square. So what I can do is I can replace this and write cosecant is cotangent 1 plus cotangent square theta. Alright, so I can replace cosecant by this thing. So I will get k cosecant square theta over a square plus k square plus k square cot square theta square root. Here it's a minus sign. You see, sine 4 theta phi prime square, and I brought it here. So this plus will become minus, this will become minus, this will become minus, minus and minus. Alright, so plus this is minus here. So with the minus sign, you will get a square minus k square. times minus k square cot square theta. Now cot square theta, the derivative of cotangent theta is cosecant square theta, so I can replace this k cot theta by some substitution. So now we need to integrate this equation. Integrating, I'll get phi is equal to integral of k cosecant square theta divided by minus k square cotangent square theta d theta. This is what you get. So now by integrating, by using substitution, of course at this level this integration should not be difficult for you guys, but if you take k cot theta is equal to, let's say, u, all right, then k cosecant square theta d theta should be equal to du. So integration becomes du divided by a constant minus u square with a minus sign here as well because integral is minus. So this is cosine inverse of u over this constant square root, right? This is the formula. Minus 1 over a square minus x square has cosine inverse x by a. So x by a square root of this thing, which is this thing. So now u, if I replace u back, then you get k cot theta divided by a square minus k square. This is what you get. All right, and of course if we integrate it, another constant will come here, so plus a constant of integration, which is c2. So now just to give it a compact form, just to give this a compact form, I can rewrite k cot theta over a square minus k square equal to cosine some function minus c2, right? You see, what is this? This was phi, right? So phi was equal to this thing. So if I bring this c2 here, it will become phi minus c2, and then take the cosine of this thing. So cosine of phi minus c2 is equal to k cot theta by a square minus k square. So I can rewrite it like this. And now cosine phi c2 is cos phi cos c2 plus sine phi sine c2. Now if you multiply this on the right hand side, you can write k cot theta, because k over a square minus k square is a constant. This whole thing is a constant. So cot theta can be written as this is constant multiplied by this whole constant is another constant. So I can write a cosine phi plus b sine phi, where a and b are given by cos c2 multiplied by this and sine c2 divided by this, right? Where a is equal to cos c2 times a square minus k square divided by k, and b is equal to sine c2. Because this is a constant, so for convenience we can write this as a and b. All right. So now I got cot theta is equal to a cosine phi plus b sine phi, because a here I can write, if I multiply this whole thing, a sine theta, let's say if I multiply by a sine theta, we obtain a cosine theta is equal to, because sine theta is cancelled, so a cosine theta is equal to, this will become a sine theta cos phi plus b times a sine theta sine phi. All right, because we have theta and phi, or theta phi are spherical coordinates with radius r is equal to a. Then you know that in spherical coordinates, x is a sine theta cos phi, y is a sine theta sine phi, and z is a cos theta. So from here I got z is equal to ax plus by. All right, from this expression I got because of the spherical coordinates. All right, so see here, we started off with this ds by d theta square term. We integrated it and got the function f. All right, by taking this f, we arrived at this expression, which is given by z is equal to ax plus by. So I gave all the details now on the board how we achieved this relationship, which is the equation of a plane. Now in x, y, z axis, any linear equation in x, y, z gives you the equation of plane. This is an equation of plane, and this also passes through the origin as well. Why? Because when x and y are 0, z is also 0. So this is the equation of plane that passes through the origin. All right. So it means an origin is the center of the sphere. If you remember our sphere of radius a, we took 0, 0, 0 as the center of the sphere. So it means this is a plane which passes through the center of the sphere. So your geodesic is a great circle here. Right? Why great circle? This plane cuts the sphere along a great circle, hence the great circle is the geodesic on the sphere. So we know that what is the great circle? Great circle, on the sphere you can make many circles. If you intersect a circle with a plane, it gives you a circle. If you intersect your sphere and a plane, it gives you a circle. But if that plane passes through the center of the sphere, that circle will be called a great circle. All right, it means if you are taking the shortest distance between 2 points, that curve should be the intersection of the plane which passes through the center. It means your shortest distance will come from the geodesic, and the geodesic is the great circle for the sphere. It means if you have to find the distance on the sphere between 2 points, you have to make a circle through these 2 points such that that circle is passing through the center of the sphere. All right, that gives you the shortest distance between 2 points, and that is the geodesic. So it means the sphere of radius a, the geodesic is a great circle. All right. Now determine the equation of the geodesics on the right circular cylinder of radius r. Right circular cylinder of radius r. Now it's a cylinder, and you want to achieve the minimum distance between 2 points on the cylinder. All right, and this is a helix. If you make a helix on a cylinder, that gives you the shortest distance, and we can prove it here. The geodesics on the surface are helix. So solution. Now because we are on a cylinder, it's better to use the cylindrical coordinates instead of x, y, z, or instead of spherical coordinates. So in r theta z, our ds square is dr square plus r d theta plus dz square. Again, if I fix my radius at r is equal to a, then dr is 0, and you will be left with this thing only. All right, so this is your ds by d theta, which is the differential of arc length. If you integrate this with respect to theta, this is what you will get. Now our f is this. This is my f of theta and z bar. Theta, z, and z bar. All right, so z is not explicitly there, so partial f by partial z will be 0, but partial f by partial z bar will be there. All right, so if I use this expression, my Euler equation will give me this thing. Partial f by partial z bar equal to 0. What is partial f by partial z bar? It's just z bar, not bar, z prime. Derivative is z prime. Z prime over a square plus z prime square root. So if I replace it here, I got this thing, and now z prime is dz by d theta. Again, integrate with respect to theta, I will get this thing. All right, so this is very simple calculation. The hard part of the sphere, I did it explicitly. I can leave this. Only few steps are missing here, not all the steps. All right, so you can easily convince yourself how we got this expression, and then after integration I'll get this expression. All right, so now your z is given as theta. It's in a cylindrical coordinates. So integration of this equation yields the equation of geodesic, which is a circular helix. It's a circular helix. Z is equal to constant times theta plus c1. This is a helix, and r is fixed at a. All right, if you want to find this expression in terms of x, y, z coordinates or parametric form, then this should be x is equal to a cos theta, y is equal to a sin theta, and z is equal to just theta. All right, constant times theta. So this gives you the helix on a circular cylinder. So it means if you want to find the shortest distance between any 2 points, you have to follow the helix. All right, you will get the shortest distance. If you don't follow the helix, that will not give you the shortest distance. So the geodesics on the right circular cylinder are the helix. All right, so this was another interesting example. We considered the plane, we considered the sphere, we considered the circle, and we are getting the geodesics over there. All right, you might have obtained these geodesics in differential equation course, or if you have to take the geodesic differential equation course in the future, then you will see these geodesics again in that course. So the last example is invalid variational problem. Sometimes our variational problem that we model is not a valid variational problem. All right, so sometimes you encounter these type of examples as well. So let's see one of them. I thought it should be interesting to note this type of example, that it's not always the case that variational problem gives you the answer. All right, so let's see this thing, and then I will wind up the lecture and I will wind up the course as well. So example is, test for an extremum for the functional I of y of x 0 to 1 xy plus y square minus 2y square y prime dx. Let's say this is any functional where you have a function of x, y, and y prime. These are the end conditions. Here our function is this. If I differentiate this with respect to y and with respect to y prime, I'll get these two expressions. My Euler equation will take this form. Partial f by partial y minus d by dx of partial f by partial y prime will give you this equation. Y is equal to x by 2. All right. However, this function does not satisfy the given boundary conditions. I got y is equal to x by 2, but y at 0 is not 1. At x equal to 0, y is 0. All right. And at x equal to 1, y is 1 by 2. So our end conditions are not being fulfilled here. All right, so that is 1 is equal to y0, which is not equal to 0. It had to be equal to 0. Similarly, your 2 is not equal to minus 1/2. So thus an extremum cannot be achieved on the class of continuous functions here. All right, so what functions we are getting here? Our extremum cannot be achieved. If I change the boundary conditions here, that y at 0 is equal to 0 and y at 1 is equal to 1 by 2, then it is a valid problem. All right, so then it will become a valid variational problem. So it depends, not only the Euler equation, it should also satisfy the end conditions. If end conditions are not being satisfied, then you are not getting you are not getting your solution curve, which satisfy your Euler equation as well as the conditions. So to get the valid answer, you should satisfy both the Euler equation as well as the conditions. All right. So today we continued with the variation of Today we continued with the calculus of variations, and we saw more variational problems in that topic. In particular, minimum surface area, solid of revolution with least resistance, geodesics, and we found out 2 types of geodesics, and then invalid variational problem. So this was it with the calculus of variations, and this is it with the course as well. So thank you very much for being with me, not for this lecture, for the whole course, about 32 lectures. I hope you understood the course and will be available for your help, no problem at all. You can also contact your instructors here at the virtual campus. They will help you as well. And I hope you enjoyed the course, and I hope you learn from it. And again, I hope this course will help you in your future courses and in your future endeavors. I wish you very best of luck in your future with your current MSc Mathematics and for the future as well. And that's all from this course, and that's all from me. So I'll take your permission to leave. Thank you so much for being with me, and wish you best of luck. Allah Hafiz and Assalamu Alaikum.